Good morning, everybody. I posted the topics, right, for the exam we're taking a week from right now, right, next Thursday. I organized them by chapter, even though that's not the order they'll appear on the exam, right? So just make it a little bit easier for you to identify what's going on there. But everything's going to be as you experienced it before, right? Same format, 7 questions, 70 minutes. It's the same exam autopsy when we're done. Really just focus on learning the process. It's all about process in this unit, more than having a toolbox. Toolboxes will help you a little bit, but more it's about generating and sticking things together. As a general study plan or strategy, right? Because we're covering chapters 4, 5, and 6 on this exam. What would you say is the hardest topic of this unit? The problems that take the most time and effort. Chapter 4, Newton's second law problems, right? So you can do this one of 2 ways. You know at least one of your questions on the exam will involve that, right? I think I said static equilibrium in the topics, but you did some in the homework. And so you can say, okay, leave that one for last, right? Since I know it's going to be long and a lot of work or something, right? And it's 1 out of 7 questions, right? So budget your time and study the parts that you think you can get, right? And be clever about how you spend your time studying and all that kind of stuff. Don't put all of your time into one question, right? When there's 6 others that you got to get on top of. All right, we were doing this inclined plane, right? And we did this yesterday in lab with Newton's laws. And you guys got to put together all of those free body diagrams and things like that. We were doing it with conservation of energy here. And just to review just slightly, we start with the master equation. And then we start figuring out its parts. We figured out the final energy. We asked questions like, is it moving? Does it have kinetic energy? Does it have gravitational potential energy? And we said no at the final point because it's down here, right? And then we did the same process with the initial energy. This is the initial energy term, right? All the combined energies it has at this initial point up here. And we were part of the way to figuring out this work. Remember, work is force times distance. Why does this work have a minus sign on it? It's friction. It's kinetic friction doing the work. And what's one thing we know about kinetic friction? It always goes against or opposes motion, right? So kinetic friction is always going to be causing negative work, right? It's FD cosine theta, but the angle between the friction, right, and the direction this thing is going. They're all lined up, so we don't need to worry about the angle. So we got to this point. We got to this statement. This line right here is a cleanup, right? It's cleaning up this line right here where we had some stuff that were zeros, right, and all that kind of stuff. But our goal that I stated last time, our goal was to find the coefficient of friction. I don't see the coefficient of friction anywhere in this statement. So what do?
Cry.
The opposite of cry. I remember how much fun this can be. No. You guys don't like that pun at all anymore, do you? Right? Where'd that equation come from? Chapter 4, wasn't it? Okay. So the force of friction has something to do with the coefficient of friction and the normal force. Okay. So if that's the case, UND equals all this stuff. All right. So what's the normal force? Good. Yeah, we got to go back and we just got to remember really quickly that there's a component here, mg cosine theta. So just as a sort of recycled from chapter 4, your normal for an object that's just is not being like pushed or pulled in a strange way, like pulled off the surface or pushed into the surface in any way, shape, or form. The normal force is generally going to be this, right? The normal force is a reaction to the strength of gravity acting into the hill. If you're flat on the surface of something, then the angle's 0 and it's just mg. But as the surface tilts, the normal force gets less and less and less until it's vertical, in which case the normal force is 0. So we can just go ahead and substitute that in. And away we go. Physics over. Math begins. Is there something I can get rid of in every term? Mass. So divide every term by m, goes away. Then I'm going to, just because I can right now, I'm going to say that's a plus, this is a minus, and this is a plus. I multiplied every term by -1. And then I'm going to divide by GD cosine theta. So mu is going to be 1/2 V final square, the minus sign in front of it, plus GH initial, all divided by GD cosine theta. Yep. Okay. Now, we'd have to know this initial height right here, wouldn't we? Like where this thing starts. If all we're given is the angle of the hill and how long the hill is, d, how do we find that height? Why did we use sine? It's not touching the angle. So height initial would be d sine theta, and now we've got all the pieces that we need. If let's say the angle were 40 degrees, the velocity final was 28 meters per second. I don't know why I put squared. That was dumb. And the distance down the hill was 100 meters. And you put that all in there, you would get a mu of 0.32. And why did I not put any units on that one? Yeah, it's unitless, okay? So I invite you during your studying to compare and contrast this approach that we've just done with what we did back in chapters 4 and 5. Right? Chapter 4 and 5, like yesterday in lab, there was no friction yesterday, but there was still a lot of free body diagrams and a lot of math, right? And a lot of Newton's second law. Lots of places to trip up in Newton's second law with the signs and the template and all that kind of stuff. And here, we were able to do the same problem. 1, 2, 3, 4, 5, 6 lines, right? By setting it up with energy. I know it feels difficult and it feels overwhelming and oh my gosh, there's so many equations coming together. Again, don't focus on the equations themselves, focus on the process, right? And why the choices were made the way that they were made. But in nearly every case, using conservation of energy is faster and less error prone than doing it any other way. Physicists, when observing something in the universe or being given a problem of any kind, our first assumption, our go-to toolbox, is actually not this one. It's called simple harmonic motion, which we'll study at the end of this semester. Okay? We will first try simple harmonic motion. The reason we will do that is that the simple harmonic motion toolbox is based on energy. If we didn't have simple harmonic motion, we would assume conservation of energy and we would start there. And then if we found out that that wasn't working, then we would reach for kinematics or Newton's laws or something else, right? Just as a point of entry, when you can't figure out how something works, in physics, start with energy, right? Historical example of this is physicists were trying to figure out what atoms were, okay? Chemists were trying to do the same thing, but chemists went weird. kind of a joke. You'll see. You go tell your chemists that I think they're weird. They'll laugh. Physicists looked at an atom and went, what if it's a spring? An oscillator, right? What fell out of that assumption is called quantum mechanics today, right? Okay? And quantum mechanics is the most powerful model that we have to predict what the universe is actually doing compared to any of these things. So energy is where you start, okay? Now, energy, conservation of energy cannot tell you anything about acceleration. If you need to know the acceleration of something, or you're given the acceleration, you're using either kinematics or Newton's laws. Energy also doesn't tell you anything about time. Notice there was nothing in here about how long this took. And so if time is important, you're doing kinematics. If acceleration is important, you're either doing kinematics or Newton's laws. But if you don't worry about acceleration or time, you're doing conservation of energy. It's just, it tends to be faster, quicker, and overall mathematically easier. So let's tackle a problem which, if we had to do with kinematics and Newton's laws, would take forever. In fact, if all we had were kinematics and Newton's laws, we would not be able to do this problem in this class because it would require calculus to do. When a jumper jumps out of an airplane, ideally with a parachute on their back, what happens to their acceleration?
Slows.
It gets less and less. It starts free fall, but then the acceleration gets less and less. Why? Before the parachute's even opened. Air resistance, right? So we could pretend and we'd say, no, there's no air resistance and blah, 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 blah. But like that's not reality, right? We're going to do the real problem. In order to pull that off with kinematics, to have a acceleration that's constantly changing, we'd have to reinvent the kinematics toolbox with calculus. Calculus is able to handle things that change, and calculus allows to add up all the little changes. It's the power of calculus. We can't do that in this class because this is an algebra/street class. Calculus not allowed. So what we're going to do is we're going to use energy instead. Right? We're going to use energy to see if we can kind of get around this problem of the acceleration not being constant, of there being air friction and all these other things. Because, quite frankly, I don't want to do Newton's second law either when it comes to changing forces and all kinds of stuff, right? Because the force changes in here, doesn't it? Before the parachute's opened, you've got one air friction. After the parachute's opened, you got another. I mean, parachutes exist to increase air friction, don't they? It's like their whole point. Slow the skydiver down so that they don't hit the ground going faster than about 5 meters per second. 5 meters per second is about 10 miles an hour. So you can survive above that, but above 10 miles an hour, you're starting to run the risk of breaking bones and things like that.
Is that, what's the, you said the final velocity? Or
Mm-hmm.
velocity?
The velocity that you hit the ground.
Are you referring to that's the maximum velocity that they can go with that from them jumping from the planes?
No, it's the velocity you don't want to really exceed if you want to have a safe landing. In general. I mean, of course, stunt skydivers can hit the ground faster, but their bodies are trained for impacts, right? I went skydiving once, and I told my instructor that I don't want to exceed 5 meters per second. He looked at me. I said, I don't want to land faster than 10 miles an hour. He's like, oh, yeah, no problem. It was painful. Skydiving was painful.
Sounds thrilling.
It was exciting. I had a lot of fun. But what they don't prepare you for is the noise. Nobody ever told me about the noise. They told me about the jumping out of the airplane and not being afraid and you're not going to die and all that kind of stuff, right? You exit that airplane and there's just a wall of noise. Your ears shut off. It's so loud, right? And the peace only returns after the parachute is opened. And the parachute opening hurt my back. So have kind of a negative. Not permanently, but it did hurt. All right. What do we got? First step. First step in any physics problem is to do what?
Conversions.
No.
Identify.
Visualize, right? Identify things. Try to get your information organized. I'm going to attempt a picture. Okay, and let's see, so like right at this point,
Is it a skydiver?
it's supposed to be, right? I'm trying here, guys, I'm trying, right? Okay, triangle, should have drawn a triangle, right? Right? Should have stuck with the simple shapes, right? Okay, what do I know about how high it is up here? 1,000 meters. And where's this dotted line? 200 meters. This is going to be 0 down here at the ground. Okay. I'm going to attach some other information here. I know that the force, like the air drag, force of air drag here was 50 newtons, right? And then after the parachute opens, I know that the force in this section is 3,600 newtons. Okay, so let's see. I got and the mass. I can write down the mass of the skydiver, right? 80 kilograms. Check my units. Looks like everything's in meters and newtons and kilograms. That's good. Okay, part B's got a different number in it, but I'm not going to worry about that because I'm doing part A. Part A first. Okay. What are they asking me to find in part A? VF equals question mark. So I'm just going to write that and circle it to remind myself that that's what I'm after, right? How are we going to do it? When all else fails, use energy, right? And this is an example in the energy chapter, so it must be, it's got to be this, right? This is a choose your own adventure. What do you want to do first? Work, energy, which one? Doesn't matter. Energy? Okay. So work, we'll leave on the side for just a second. To be able to do energy final and energy initial, I need 3 things. What 3 things?
Acceleration, time.
Nope. Nope. What 3 things? Nope. Nope. There's 3 things I have to decide.
The initial.
Initial, final, and 0. You can't get any traction into figuring anything out unless you know those things, right? So where's the initial point? Let's do it up here at the top. Again, when you're picking these things, either go with what feels sort of natural, like is an object starting somewhere? Then that's probably the initial point, right? Okay. What about the end? Where are we going to put the final point?
0.
Let's put it at 0. That's where we want to find out how fast they're going, right? And I know some of you are like, but wait. Doesn't it change at 200? Shouldn't I put my final point at 200 and like do the first part of the problem and then do a second part of the problem, right? And then find it? No, energy can handle it all. I'll show you how. But energy can handle this all. So let's put the final at the bottom. Where are we going to put 0? Lowest point in the problem. I already put 0 there. Good for me. Okay. So let's see here. I'm going to back up, do this in red. Work, non-conservative. Energy final. We're going to laser focus on this point right here. And we've really got to ask 2 questions. Is there kinetic energy? And is there potential energy? Is there kinetic energy at the final point? Is the skydiver moving when they hit the ground? Yes. In fact, that's what we're trying to find, right? This V final. So we know they're moving. We don't know what the number is. We're going to try it. That's going to be the thing we're going to solve for, right? And is there any potential energy?
No.
Why not?
There's no height.
There's no height at the ground, right? We put 0 at the ground. They're at the ground. And so my MGH initial, this whole term is 0. You can either write MGH initial and then cross it out, or you can write potential energy and cross it out. Sometimes if you just write plus 0, it's not enough for future you to realize what you did. So again, you're trying to leave breadcrumbs so that you can go back and see what choices you made. So figure out some way to make notes to yourself, right? You could come over to the side and say like, final kinetic energy, yes. Potential energy, no. Right? Whatever system works for you to keep track of, what you're doing, do it. Okay? This is what I do. Okay, minus, and then we've got to do the whole amount of initial energy, right? So, initial, if I'm doing it this way, do I have kinetic energy initial? No, we're going to assume they fall out of the airplane. Technically, the airplane's moving sideways, but don't worry about that. Okay? So, this is no, and potential energy initial? Yes. Right? So, if it has no kinetic energy, and sort of my method would be 1/2 mv initial squared and then cross this out, plus mgh initial. Okay? All right, and then I typically do the next line at the same time. Like, I've worked out the energy, so now I'm going to work out the force, and I'm going to clean up the right-hand side. Okay? So, to do the work, what do we need to ask ourselves?
Why?
Sure. Try not to ask why too much inside. It's more of a philosophical question.
Which forces?
Science concerns itself with how, what, when, and where.
Forces?
Yeah, we need to start asking what forces other than gravity exist here. Right? So what's the answer?
Fun.
Air resistance?
Air resistance. You're not far off, right? But we're not actually going to use fun this time. This is no fun.
Oh.
The reason being is that they've already told us the forces. Like I don't need to go find a coefficient. I'm not worried about a normal force, right?
Oh, yeah.
It's just they told me the force already, so I don't need to break it down any further. But how many air frictions do we have?
2.
2. So this work non-conservative is going to be the work from force number 1 plus the work from force number 2. That work non-conservative term is you add up all the non-conservative work you have in the entire problem. We've got 2, right? And we'll work out what those are. So this is 1/2. I'm just cleaning up this side over here. V final minus mgh initial. Okay. So what is work from force number 1? Work is always what? Force times distance. Cosine theta, but this is all lined up. Okay. Air friction, positive or negative work?
Negative.
Acts opposite, right? Okay. So I'm going to write minus F1 D1. What's D1?
Distance. 1.
What is it?
800.
It's 800 meters, isn't it? Okay. And what's D2? 200 meters, right? We broke up the 1,000 meters into 200 and 800. Okay, so plus, we're adding these works together. They just happen to be negative things. Minus F2D2 equals all of this stuff on this side that didn't change. Let's do a check. Do we know what F1 is?
50.
Do we know what D1 is?
800.
Do we know what F2 is?
3,600.
You can just say yes or no.
Okay.
Yes. D2?
Yes.
Yes. 1/2.
Yes.
Mass.
Yes.
V final.
Yes. No.
Oh, this is our unknown, right? Do we know this mass? Yes. Do we know what planet we're on? Yes. Do we know how high it started? Yes. So there's only one unknown in this entire thing, isn't there?
Yes.
So let's solve for it. This is going to be minus F1D1 plus F2D2. Doing fancy math over there. I factored the minus sign out, right? And then I'm going to add MGH initial. What am I doing right now?
Math.
Doing math. Everything after the dotted line is maths. Okay, right? I moved the MGH initial over to the other side. And I also factored a minus sign out of my work terms. Okay? Now I've got to multiply both sides by 2. Where did that come from? Getting rid of the 1/2 and divide by m. And then take a square root. Hope and pray that I don't get a negative sign under this square root. Right? Because if I got a negative sign under this square root, that would be a bad day, wouldn't it? Okay. Why would that be a bad day? Kids, that's imaginary physics. Minus 2 over 80 times F1, 50 times 800, plus F2, 3600 by 200, plus 80 times 9.8, running out of room. What's my initial height? 1,000. I'm going to move some stuff around here. Let's move this out of the way. We'll move it up here, okay? So that I can make this look not quite as bad and make it look like I intended to do that. Okay, right? Good luck sticking that in a calculator, right? Yeah, Desmos is pretty fun. Okay, so does anybody want to guess how fast this is? Well, you calculated it already? It's 24.5 meters per second, or approximately 55 miles an hour. Most days, if you hit something at 55 miles an hour, that's considered a very bad day, right? Above 50 Gs of acceleration, the human brain cannot continue functioning. There's various levels of trauma that exist before that, but above 50 is more or less the dividing line. And going from 55 miles an hour to 0 miles an hour in a very short amount of time is definitely a lot of acceleration and would not be survivable. So what does this parachutist need to do? Not hit the ground that fast. And how are they going to do that? Open the parachute earlier, right? So in part B, we're going to alter the question, right? We're going to reframe this as, we now know what we want the final velocity to be. When do we open the parachute? So in part B, what do we know and not know?
Everything but D2.
I'm going to do this one in green. So for part B, right, we don't know D2, right?
Destiny 2.
Right? Which means we also don't know D1. Yes or no? Yeah, we don't know D1, we don't know D2. Okay. Which one are we trying to find? D2. We want to know how high above the ground to open the parachute, right? Can we recycle something? Is there an equation that's already on here that we can use again? That's still true?
Yeah, that.
Is any of this wrong?
No.
Does it still apply for part B?
Yes.
Careful. Do we still have two works? Are there still two sections of differing force? Yes. Does the skydiver still have speed at the end?
Yes.
Yes. Does the skydiver still have initial potential energy? Yes. Did we introduce new energy?
No.
No. We're just changing D1 and D2, right? So we can recycle the equation in the green box. It still applies for this situation. We just need to solve it instead for what?
D.
D2. But there's two unknowns. D1 and D2 are both unknown. And we only have one equation in the box. So what does that mean?
Factor.
Factoring's not going to help us.
We have to.
If we have two unknowns and only one equation, how many more equations do we need minimum? At least one more. You need two. You need one equation for every unknown thing you have. So if we have two unknowns, we need two equations. We only have one, so we need another equation. Oh, we don't even need really physics. Well, it's physics, but it's not physics. We just need to think and realize that whatever they are, they have to add up to 1,000, don't they? So if we open the parachute at 600 meters above the ground, automatically that means D1 is what? 400, right? So that's what this statement right here says. It wasn't like from kinematics. It wasn't from Newton's laws, right? It wasn't from some other toolbox. It's just a statement of, well, we know what they add up to. We don't know what they are, but we know that they add up to 1,000. With that in place, we can solve for D1. D1 is going to be equal to 1,000 times D2. It's supposed to be 1,000, okay? That gets put into there. And then we solve for D2. I didn't do all that work. What I did is get the answer. So that's just a bunch of algebra, isn't it? And I don't want to waste time doing more algebra in here. Frankly, I don't want to do algebra either. Does anybody want to guess where you have to open this parachute? 700? 750?
500.
500? The answer turns out to be 206 meters.
Oh, so you have to jump early.
What's that?
You have to do it early.
You got to do it earlier. You got to do it higher. But it's not that much higher, right? A 6 meter difference in this situation was the difference between dying and walking away.
So are you saying that it's 206 meters off the ground?
Yeah.
Okay.
Yeah, D2 is measured from the ground up, right? So only 6 meters of difference. It doesn't seem like a lot of room for error, does it? Okay? But if you do it before this, you're going to probably end up still going 5 meters per second, but like you're just going to have longer time, right, to get down. If I had to parachute again, probably won't again. It was good to do one time. It was good to do one time. It's not something I'd do over and over again. Only because of the noise. So if I was allowed to wear the helmet that my instructor had on, I probably would have enjoyed myself a lot more, right? Because the helmet he had was like protected his ears from the air, and all I had was like a pair of goggles, right? And I could guarantee that my chute would open more gently instead of the big jerk, right, that it did. Then I would jump out of perfectly good normal airplanes because that does sound like fun. But I would beg my instructor doing a tandem jump, as soon as we jump out of the plane, open the parachute. Because to me, the enjoyable part was the drifting down. It was peaceful. It was quiet. All you heard was this gentle wind through the canopy of the parachute. And boy, was it just fantastic, right? To just kind of circle, right? And go down. That was, you know what? I wouldn't do parachuting. I would do paragliding. That's what I would do. There's special parachutes that allow you to catch the thermals. That's what I would do. Yes. Did you catch it?
Oh, there is a dog.
What's the service person got attached to their fronts? A dog. Okay. There's a lot of reasons I'm showing you this picture. The men and women of our armed forces do some pretty amazing things. And one of them is they work with animals. Okay? These animals are designed to do a variety of missions, but this picture has always captured many feelings in me. I am a pacifist, but I also support our troops. Like, I understand that my pacifism comes at the cost and great sacrifice of others. And so I deeply respect anyone who serves in our armed forces. The dog may or may not have a choice, so to speak. They're bred for a purpose. My mother trained seeing eye dogs for the blind, but that training intersects with the training that these kinds of animals might do. Of course, military training is much more rigorous and severe than seeing eye dog training, and the applications are different. But I've worked with some of these military dogs, and they're phenomenal animals. No dog, or any other animal for that matter, is comfortable with jumping out of an airplane. They just aren't. They know better. Smarter than humans when it comes to this, right? Okay? And so in order to get a dog to jump out of an airplane, you got to do several things. And I've seen footage of dogs and their handlers jumping separately. So the dog has a parachute. Okay? That was sort of early times. They now jump together. They'll strap the animal to the handler so that they land in the same place and they don't have to find each other and all that kind of stuff.
How do the dog know when to pull the parachute?
They don't. There's a computer on there. Yeah, okay. It senses the altitude and then just pulls the parachute for them. But one of the things that special branches of our military do is something called a halo jump. The joke is, if you do it wrong, you'll be wearing a halo. The acronym stands for high altitude, low opening. And so if the desire is to get a combatant into an area that they're not supposed to be undetected, then what you do is you jump from an airplane that's very, very high up. Parachute all the way down below mountaintop level. So we're talking just 1,000 feet off the ground or something like that. And only open the parachute after you're below the mountaintop level because they're trying to avoid radar. Okay? And so it's called high altitude. That's where you jump from. Low opening, where they open the parachute. These parachutes are controlled by computer. No human being has a reaction time sufficient to open these parachutes at the right time. Parachuting in the military is the activity that generates the most injuries. Full stop. Okay? Outside of a war, okay? In training, in all of these things, people break their legs all the time. Okay? Parachuting is really, really dangerous. And so they train hard and they train well, but you're talking meters worth of difference between a landing you can walk away from and a landing where you're going to be a casualty.
Does anything involve in like the weather conditions?
Oh yes. Oh yes. Very much so. Atmospheric pressure, like the barometric pressure in the air, presence of dust, presence of clouds. Like there's a lot that goes into it. The service people that I've known that are trained in this say that it is the scariest thing that they do. You're trusting your life to a computer, essentially. The dogs, okay, have to be blindfolded. Because again, they won't, you can throw a treat out the back of the airplane, the dog will just go, are you kidding me? Right? They know better than to jump out the back of an airplane, okay? So they have to be blindfolded. They wear a mask. So the dogs need oxygen too. So they have a muzzle that's got an oxygen supply. They have part of that mask blinds the dog, right? So that they can't see what's going on. And you know that, how do you know when a dog is happy?
Wagging the tail.
Wagging their tail. A wagging tail means you are lunch or they are very happy. And usually those two feelings are the same in a dog. So they will just be wagging their tails and you watch the handler, they pick up the dog and they chuck him out the back of the airplane and then they jump after it. Right? That was the old way. Now they strap it together, they jump together. It's much less stress on the animal.
I thought you said it was like super loud when you jumped out.
It is. That's why you wear helmets.
Doesn't for the dogs though?
This dog doesn't seem to care. Right? It's probably loud for them, but they're not human beings. Their ears are different, right? They also have like big flappy ones. Mine were doing this as I was, skydiving, but that wasn't much protection, right? So, but yeah, just amazing animals, amazing humans, even if I disagree with why they need to exist. Let's do a quiz. It's been a little while since we did a quiz. Was it last class? It was the 4.1 last time, wasn't it?
It was 6.1.
Maybe it's 2B that it's been a while since I did it. I don't know. 6.3, 6.4, 2 points. So, not big money this time. This quiz may or may not be based on an actual event. I'll let you decide if I was student A or student B.
Is it only
There's only one answer.
One.
Only one. I'll give you 30 more seconds. All right, you turn to your neighbors. Tell them what you think and why. Go.
I also said D. I feel like A's a tricky one. Yeah, because they call it the same. They definitely don't have the same potential energy because they're different masses. And if they don't have the same potential energy, then they can't have the same kinetic energy at the end. Which have different conservative energy, right?
Yeah, that's why I stopped halfway.
They have
Notice I never ask students to rate their confidence on their All right, you got your answers down? Okay, why is A wrong?
because they're gonna hit.
Doesn't matter if it's energy or not. Two objects falling, right, are going to hit the ground at the same time, right? Again, we make the assumption no air resistance. Okay, why is B wrong? Oh, they have different masses, right? They're at the same height, they're on the same planet, but their masses are different, right? So they can't have the same potential energy, right? Potential energy is mgh. H is the same, G is the same, M is different. Can't be the same.
B was at the top.
Okay. Why is C wrong?
If
Because they have one has different masses.
if they have different potential energies, then.
Okay, if the potential energies are different, then the kinetic energies will be different. Conservation of energy, right? Whatever you start with, you end with. So if they're already different at the beginning, going to be different at the end. You were saying different masses. They are going the same speed. We said that in part A, right? They all hit the same speed. Everything accelerates at the same rate. Speed's the same, the half's the same, but the m's are different, right? So we could make like the same argument, right? So that means that D better be correct. Is it?
Everything else is wrong.
Everything else is wrong, and Mr. Balogh said that one of these is right. Did I lie?
D for four.
Is D correct or not?
We are going to
Why is D correct?
more force.
Twice as massive. The force times distance, right? Why does student B have twice as much potential energy?
More force.
Because student B did twice as much work. And why did student B do twice as much work?
They're heavy.
Gravity pulls twice as strong. Force and distance, right, is work. So twice the force over the same distance is twice the work. This is something I always tried to point out to my bigger friends. Right? I might be smaller than you, but you guys are doing more work. My best friend in middle school and high school, his name was John. He was about 6'3", about 250 pounds, all muscle. I was on the swimming and water polo and diving teams. He was on the football team, right? Like, couldn't get two very different sort of ends of the gene pool, so to speak, than the two of us, right? So we had a lot of fun together, though. Opposites attract. Oh, start the record.
I feel like smell.
Okay. I said earlier that if time's involved, it's kinematic. That's 98% true. We are going to sneak time in right now to energy through this concept called power. When you hear the word power, what do you think of?
Dictators.
Dictators, right? Okay. You think of political power. You think of military power. You think of economic power, right? We in our society today, like, power comes in many different forms, and in the case of our leadership, the power is being applied incorrectly. But that's politics, not physics. Although I do have data to support my conclusion. I'm going to give you some quotes about power. One of the things that they beg me to do is to try to justify the existence of the other subjects. It's called teaching across the curriculum. We've got to give, like, political science a reason for existing, and English a reason for existing, all this kind of stuff. So I'm going to give you some quotes, historical quotes about power. And I just kind of want you to appreciate how clean the science will be compared to this, right? Okay. Anybody know who Abraham Lincoln was?
Yes.
Maybe? Okay. And, of course, Abraham Lincoln, living in the 1800s, was not gender neutral in his description. So insert whatever favorite gender pronoun you want into this statement. Nearly all men can stand adversity. But if you want to test a man's character, give him power. That's deep, right? Adversity is one thing, but if you really want to find out what a person's made of, give them power. And a lot of times when they get power, their true natures come out. Thomas Jefferson. Anybody know Thomas Jefferson?
Yeah.
Sounds, yeah, maybe, right?
I think he's on a dollar bill.
$10 bill. Okay? Washington's on the dollar bill, isn't he? Famously, Thomas Jefferson is the one that Texas is trying to get removed from history. You guys know about this?
What?
In the late 90s, many school board, Texas is weird. In the 1990s, many school boards across the state of Texas were trying to remove Thomas Jefferson from the curriculum of history, like American history. And the reason that they gave was, quote, he does not reflect the values of our founding fathers, unquote.
What?
This is the same wisdom that's being used today, like by RFK Jr. and stuff, okay? Thomas Jefferson. I hope our wisdom will grow with our power and teach us that the less we use our power, the greater it will be.
Couple steps.
Think about that. Okay, this next one, okay, I don't even have to read. I don't even have to look at the quote. I can quote this one verbatim, okay? Now, what I can't do is do the voice correctly, okay? So you're just going to have to supply the voice yourself. I'm not going to tell you who it is, but I'm just going to try and see if you can guess who this is based on this quote. Are you ready? So in the entirely wrong voice, this is the quote. The power to destroy a planet is insignificant when compared with the power of the Force.
Oppenheimer.
No. Darth Vader. Darth Vader. Episode 1! The original one. Episode 4. The first Star Wars movie. They're blowing up Alderaan. Princess Leia. Yes?
Hey, Bill, I'll give you my quote. With great power comes
Great responsibility. That's another good one right there. Another good one right there. Okay. Spider-Man. Uncle Ben, right? To Peter Parker. So power is a lot of things. But in physics, it's one thing. And it's not math. Did you ever see those posters? Math is power? I hated those posters. That was so dumb. Power is work divided by time. So you can go home and say that you were culturally educated today in your physics class. You're welcome. All other subjects on this campus. Okay. Power, the amount of work that gets done per time. Now, because energy and work have the same unit, you can also say that this is like a change in energy in time. Okay? So both are fine, right? You know the unit for this one. What's the unit of power?
Watt.
It's watts. And you've probably run into that based on like your phone charger, right? I used to say light bulbs. Nobody knows what the wattage of a light bulb is anymore, right? But like your phone charger, you have like a 10-watt charger and a 20-watt charger and an 80-watt charger. What does that mean? Like when they're telling you 80 watts versus 20 watts, like practically in your life, what does it do?
Faster charge.
Faster charging, right? And so why would more wattage, more power lead to faster charging? More energy is being put in a certain amount of time, right? So the watt is a joule per second, right? So if your charger, you're looking at your charger right now, right? Okay, that's a 10-watt charger. That's a 20. Okay, it's a 20-watt charger, right? So that 20-watt charger, which is for an iPad, right? Apple charger, yeah. So that 20-watt charger is providing 20 joules of energy every second maximum. It doesn't do it all the time. Because as the device's energy, as the battery gets close to full, it will slow down and it will lower that amount of energy it sends in. In fact, the battery chemistries of today, they really don't like being charged above 80%. From kind of low, like 10% up to 80%, you can fast charge something. Batteries can accept a lot of energy really fast in that range. But below 10% and above 80%, the battery can overheat too much if it gets too much energy. And so the charging circuits in your devices are clever enough to figure out what to do. In fact, I know this is true for Apple, and I'm assuming it's true for Android. I don't have any Android devices. There's a way to go in and tell the phone, like, don't go past 80% on a regular basis, right? A lot of phones nowadays, they sort of learn your habits as far as like, when are you using your phone most often? When do you charge your phone, right? And it will try to predict, oh, they're plugging me in at a normal time, I better charge up full. Or, oh, I'm getting charged at a non-normal time, maybe I only trickle charge a little bit. All in an effort to try and keep your battery chemistry happy and keep your battery lasting longer. So there's a couple things here, okay? What's work? It's force times distance, isn't it? Okay. What's a distance divided by a time? It's a velocity, isn't it? So another way to write power is force times velocity. If you know how fast something is going, and you know how much force is required to keep it going at that constant speed, then you can figure out how much power is being consumed. There are other units here, okay? And I've mentioned them kind of before, right? The one that most people think they know is the English system of units when it comes to power. What's the English unit of power? No? Horsepower. Right? You don't ever walk into a car dealership and say, hey, how many kilowatts is that car engine, right? Okay. I do that because I'm a nerd, right? Actually, if you're into any kind of motor sport, so be that F1 or rallycross, right? Some of these more international, not NASCAR. All of the teams will reference the car's power output in kilowatts, thousands of watts, right? Because it's the SI metric system it's the unit for the SI system. What's a horsepower?
How fast a horse moves?
Power relative to a horse.
Yeah, like what kind of horse, right? Like when James Watt, of this unit's fame, was trying to communicate to people about his newfangled steam engine, right? And trying to sort of sell it or market this idea. Because what he was doing, he was going to like mining operations and saying, look, my steam engine can do the work of like 10 of your horses, right? He kind of standardized around this idea of how much a horse, how much work, how much power a horse can do. The horsepower is defined as 550 feet-pounds per second. This is equivalent to 746 watts. So there's your conversion factor between horsepowers and watts. But a horsepower is 550 foot-pounds per second. So think of a horse connected to like a pulley, and it's lifting a 550-pound mass, right? Straight up. Horse walks forward and it lifts up, right? This pulley mass. So 550 foot-pounds, 550 pounds lifted through a distance of 1 foot in 1 second would be equivalent to a horsepower. Now, for some reason, my computer has decided to shut everything off. So let's try and get it back. I was saying, I mentioned the word Android in front of Apple devices, and it just decided to quit. Well, I have a feeling that this particular error that just happened is going to require a reboot of the laptop. Yep. Okay. So what's going to happen is we are going to pivot. Let's disconnect that. I know how to fix it, just give me a second. The YouTube, however, is only going to have audio from this point on. Yeah, I know you're unable to connect. Try again. Oh, this is a more serious error. Like super crash. Mega crash. Where? Don't worry, I have backups within backups. I'm wondering if the AirPlay thing died in the podium. YouTubers, I will try to get this to work with all of the video, but it may not. You guys see my iPad? Yep. All right. So we'll always prioritize the people in the room in front of you. I love you guys. YouTubers, come to class. All right. 746 watts, 550 foot-pounds per second. Is a human being capable of a horsepower?
No. Train hard enough.
Can a human being lift 550 pounds of force through a distance of 1 foot in 1 second? Not without ripping their spleen.
On average.
Right? But can a human being lift 225 pounds through 2 feet in 1 second? Or 112.5 pounds through a distance of 4 feet in 1 second. All of those were equivalent works, weren't they? Because 112.5 times 4 is 550. Okay? So the answer is yes. Human beings are capable of a horsepower. What's the difference between you and a horse?
Breathe.
I mean, okay. That was a loaded question, wasn't it? Right? Beyond the obvious anatomical differences, what's the difference between you and a horse?
We can't provide as much power as efficiently.
We can't do a horsepower for like 8 to 10 hours a day, right? We can do a horsepower for very short periods of time. If you ask us to do it for a long period of time, we die. If you ask a horse to do a horsepower, what does the horse say? Okay. I've worked with horses. Okay? They're intelligent animals. They're just not very smart. Just laying it all out there. Okay? Horses generally are happy to do what you tell them to do as long as you feed them. Right? Give them some alfalfa, give them some oats. I'll work all day long. Right? They love it. Okay? I'm still hung up, though, on what kind of horse. Because I've ridden, like, Icelandic ponies. Just big dogs. Like, literally, the horse was there, and I just went, right? And I was on the horse, right? I've worked with Belgians. Belgians are, like, they're very closely related to the kinds of horses that you see in the Budweiser commercial, right? With the big horses that, going along, right? I think a Belgian is the horse, not the person, is an elephant wearing a horse costume. 2,400 pounds of horse. Try to put a harness on that thing, right? Okay. They're draft horses. They pull stagecoaches and other loads. And I once tried to ride one, and I couldn't get my legs around it, right? And it wasn't used to a saddle anyway. It just turned its head backwards and looked up at me like, what are you doing on my back? And I just stared at it, and I was like, I'm going to do this. And it was like, Okay, as long as there's alfalfa, right? I ended up sitting cross-legged on its back, right? Because I couldn't get my legs around. There's a big difference between an Icelandic pony and a Belgian, right? I've ridden Mustangs, I've ridden quarter horses, I've ridden all kinds of horses, and they do different things, and Mustangs are dumb. They just have different intelligence and all that kind of stuff, and I'm telling you, there's no correlation between the horsepower and what these animals are capable of. Power, right, can be calculated either by doing, right, that work divided by time or force times velocity. So let's do an example, okay? I'm an airplane nerd. I love airplanes. And this is one of the airplanes you may or may not see taking off out of Fresno. We have a lot of flights in Fresno that are from Southwest now, and United and Delta. United and Delta tend to do smaller planes. This is an Airbus. This is a European plane. It's kind of beating the pants off of the Boeing planes right now in terms of performance and economy. But we're going to find out what power output its engines do in order to maintain its flight, okay? So we know the force of the thrust, and this is combined. We'd have to divide this by 2 to get a single engine, right? But we're doing the total power output of the engines, okay? So we know the distance it flies in 1 minute, okay? So how are we going to calculate the power? Power is work divided by time, or it's force times velocity, okay? So what have we got here? Like, what version of this are we going to use? What are we going to do with the 14.6 kilometers?
Convert it to meters.
We got to convert this to meters. So this is 14.6 times 10 to the 3 meters, right? What are we going to do with the 1 minute? Convert it to 60 seconds, okay? So we got that, right? So either way, like, we could do this either way, right? We could find the work, it's force times distance, and then divide by time. Or we can find the velocity and multiply by the force. They're going to be identical. So I'm going to do force times velocity. My velocity is going to be distance divided by time. That distance, 14.6 times 10 to the 3 meters, all over 60 seconds. One thing I failed to do was bring my notes over to where my iPad is. I didn't do any of the in-between calculations because I never do. I always put them together when I'm done. So that's my velocity, and power is going to be my force times my velocity. 640 kilonewtons is 640 times 10 to the 3 newtons. Okay, so 640 times 10 to the 3. Velocity is 14.6 times 10 to the 3 divided by 60 seconds. Gets me 155 times 10 to the 6 watts. This is 155 megawatts of power, which is equivalent to 209,000 horsepower. Jet engines are amazing, okay, in terms of their power output and the efficiency that they have when operating at high altitudes. Jet engines' efficiency is much lower at lower altitude. We'll get into efficiency when we start talking about thermodynamics. But at sea level, you don't see jet engines running power plants because they're just not that efficient. They were really good when they're at cruising altitudes where the air is thin, the temperatures are low, and you really need to push in order to get places.
What was the answer to the thing?
What was the answer to the thingy? Combined power output, 209,000 horsepower, or 155 megawatts. Technically, this box right here. Right? I had another example, but I think instead I'm just going to let you out early. This was an example of just, if I had time, doing another conservation of energy example, but we've had enough, and you've got enough to be able to do your homework. I posted the exam topics. If we're here to start class, I posted the exam topics. They are on Canvas. I'll be there tomorrow in draft for any help that you require. I will see you, if not tomorrow, next Tuesday. What's happening next Tuesday? The review for the exam. What happens during the review? You ask me questions, right? I'm done with asking you questions.
RASP is 7 to 11, right?
7 to 1. I'm there from 7 to 11.